All right, so the first major class, and really the most major class of aromatic reactions are these electrophilic aromatic substitutions. And you can glean from the name what the reaction is going to look like. So let's take a look at a reaction with a regular alkene. So we have an addition reaction here. We have alkene, in this case, reacting with a Br2. And what we're going to have is our alkene attack our bromine and then kick off this other bromine. Sometimes you may see this bromine coming back with its lone pair as well, depending on who's drawing the mechanism. Anyways, what you end up here with is this brominium ion, and then of course a bromide. And so if we look at our components, right, we always want to be able to identify the nucleophile and the electrophile. So right here is our nucleophile, right? It's positive loving, it's electron rich. And then our two BRs are then our electrophiles. And electrophile is, of course, negative loving and generally has at least some kind of partial positive charge. In this case of these two BRs, as this alkene approaches, the electrons induce a dipole, and so this ends up being partially positive, and this bromine is partially negative. But in most of these reactions, you should be able to identify the nucleophile and the electrophile. And most of organic chemistry is the nucleophile attacking the electrophile. But as we said, aromatics are different. And so if you take an aromatic system like benzene and just try to add Br2 to it, you will get no reaction, right? If we want a reaction to occur, we need to either make the nucleophile or the electrophile stronger. And so that's what we're going to do in this electrophilic aromatic substitution. We're going to add some kind of electrophile, and we're going to add it into, or substitute it into, our aromatic ring. So let's go ahead and take a look at the general mechanism. So we'll learn a whole bunch of different reactions, but they go through all the same general mechanism. So we really only need to know one general mechanism. So the first thing we have is our benzene ring, and what it's going to do is going to attack our electrophile. This electrophile has been activated in some kind of way to make it more reactive. We'll learn about the ways later on. And so what we're going to have is our double bond from our aromatic ring attack our electrophile. If we think about what's going to happen here, we're going to be left with a cation on one side and then the electrophile added to the other. If we think about this carbocation, the reason that it can form, it is because it's resonance stabilized. And this is called the sigma complex. Right? It's our intermediate in our EAS reactions. All right, so now what we need to do is we need to regenerate our aromatic system. And the way we're going to do that is basically just an elimination reaction. So don't forget that there are two protons on each one, or each carbon has one proton. And so these protons are still here. And so what we need to do is we need to get rid of this lower proton, so that way we can reform our system. And so what's going to happen here is a base is just going to come in and do an elimination reaction, right? So it's going to attack the proton, and then the carbon-hydrogen bond is going to break and become a carbon-carbon pi bond. And then at that point, we have regenerated our aromatic system. We can also think about this in terms of our reaction coordinate diagrams. So we've got G here, reaction here. Over here, we've got our aromatic ring and our electrophile. It's going to then go form its sigma complex, which will be the intermediate. And then this is going to be the rate determining step, right? Forming this sigma complex is the difficult part. Once your sigma complex is formed, to regain the aromaticity is very quick because we're going into a more stable compound. So overall, you definitely want to know this mechanism. We're going to learn a bunch of reactions, but the mechanisms are all the same. One thing to note about this mechanism is just be careful which proton you're taking away, right? So when you have your sigma complex, just going to draw it twice here. Make sure that you deprotonate the correct proton. So for example, if you try to deprotonate this proton up here, we would break the octet rule on this carbon, right? So that is not the correct proton to take. What you want to do is deprotonate the proton where the electrophile has been added. To form the correct aromatic system. So be careful or know this mechanism.